With that, let me introduce our speaker. Joe Laskowski is currently the Executive Director of the Institute for Laboratory Automation. Welcome back, Joe.
Thank you, and welcome to the second in the webinar series about lab automation. Last week we talked about the major elements that go into a laboratory automation system and issues. This week we're going to be talking about what lab automation is all about and why it's important. The main reasons people get involved with laboratory automation is when it's properly implemented. It will reduce operating costs, improve data reliability. It'll help you offload routine tasks and allow more efficient operations. Lab automation is really a transformational technology for lab operations. It really changes the way laboratory work is done. It changes it as much as when we moved from manual measurements to instrumental systems. This chart goes back to 2008, a survey that was done by then the Association for Lab Automation to show the growth in the industry and how important it is. And even though things have gotten really interesting economically since 2008, the numbers still hold the same. Here it shows, for example, that 12% are going to use the same level of automation and 88% are going to use more. A colleague of mine actually sent me an email a couple days ago and had some interesting numbers on it. There was a report done by Global Industry Analysts Incorporated about a new report they have out. And it indicates that the worldwide laboratory automation market is expected to reach $4.1 billion US by 2015, that the laboratory notebook market is going to be $284 million by 2017, and the LIMS market is going to hit $1.4 billion by 2015. So this is a growing market. It's getting a lot of attention and a lot of interest from vendors and customers alike. The reasons people get involved with laboratory automation, besides the ones I've noted, are these: increased productivity, improved data quality, reducing operating costs, improving safety, improving working conditions. And as you're going to see over the next few slides, the reasoning behind getting involved with laboratory automation are the same reasons that people get involved with automation in any type of environment. One of the things we also have to keep in mind is that lab automation is not necessarily needed by all laboratories. There are some situations right now where laboratories really don't get involved with it. In some cases, it's the nature of the testing. There are equipment issues. There's also issues when looking at increases in sample volume as to whether or not it's a temporary spike that might be better handled by outsourcing, or maybe it's a long-term trend where automation could be a factor. We're also at a point where test methods haven't quite caught up with automation capabilities. We have to look at it and determine whether or not there is something about the test method that precludes automation. Most methods are designed, as we pointed out last week, most methods are designed for human use, and they haven't been adapted for automation. Automation, they may not be able to be, and it's possible that including an automated system may impact the results of the test method. One concern is whether or not automation is a realistic solution to productivity issues. Is it worth the investment? As we pointed out, automation equipment is inevitable. It's coming out. It's coming from most vendors in one way or another. People may have concerns about what to automate and when and the level of automation to get involved with. And we also have to deal with changes in job descriptions and how people's jobs are going to change. We can get some guidance in these issues by looking at two areas where automation has been widely used. One is clinical chemistry, and the other is contract testing. Clinical chemistry has gotten involved with laboratory automation to the extent where they actually have total laboratory automation programs. The reason for it is back in the 1980s, a problem developed. The cost of testing was going up, the amount of testing was going up, but there were contractual obligations that limited how much a laboratory could charge for its work. So something had to be done. What was done was the introduction of automation. But they did it in a planned way, and they did it in an industry-wide way. making sure that the systems were well developed for automation, and also putting into place the standards necessary to make sure that automation could be successful. The results of that work look like this. This is work that came out of Mount Sinai Medical Center. Between 1965 and 2000, the Consumer Price Index increased by a factor of 5.5. During that same period of time, the number of samples being processed increased from 10,600 per employee per year to over 104,000. When you look at it in terms of the cost per sample per test decreased from 79 cents to 15 cents per test. This information from the Ohio State University shows similar improvements because of automation. TLA stands for Total Lab Automation, and if you're not familiar with the term, FTE stands for full-time equivalents, or basically one person's time. As they moved from their pre-Total Lab Automation work to their initial phase of implementing it, they saw a drop of 19% in the manpower required to get work done. In terms of volumes, the tests went up only between 2 to 4%. When they look at tests per FTE, or per hour, they saw an increase of 27%. And in terms of specimen processing, an increase of 72%. Again, lab automation done properly is an effective tool. Lab Manager magazine, which is a partner in this program, has a tagline on its magazine cover: to run your laboratories like a business. Well, we talked to some companies that actually run their labs as a business. One of them, a particle testing laboratory, said that lab automation was very important, that they couldn't run the operation without it. A medical and pharmaceutical testing laboratory reported that in addition to their current headcount, they need several additional chemists just to carry the workload without lab automation. And without automation, their prices would be 2 to 3 times higher per test than they currently are. Spent a fair amount of time with a particular biomedical testing laboratory to look at how automation was being done and how they actually went through the analysis of projects. They agreed that automation was key to their staying in business. They can't achieve the combination of throughput, pricing, and profit without it. If they had to rely on manual testing, it just wouldn't work. They spend a lot of time analyzing test methods to determine their suitability for automation. They look at everything from how samples are being submitted, the format of the samples, how samples are being logged. So even in the submission process from their client, they look at optimizing things. Then they look at how samples are being processed and how reporting is done to look at how to streamline the entire operations. So again, automation isn't simply a matter of buying another piece of equipment. It's really a matter of process analysis. Coming back to the reasons why people give a look at automation, one of the things I want to talk about just very briefly is improvements in data quality. People may wonder why automation improves it. If you compare it to manual methods, when people work on things using a pipette, using any piece of equipment, there are small variations in the way they do things. And over time, those variations add up to a widening of the standard deviation for sample measurements. But you expect automated systems, whether it be robotics or computer systems, to do exactly the same thing time after time. Same volumes, same measurements, and as a result, we get improvements in data quality is what people are looking for. These are the driving factors, again showing up in that 2008 survey, that people look at to drive the issues of automation. And they're the same issues that are going on today. Increasing workloads, reductions in budgets and staff, the need for outsourcing to fill in where current staff or in-house staff can't do the work, and the fact that the science is becoming more complex, and they're looking for automation to deal with that complexity. The bottom two items also deserve some attention. There's a need to streamline operations, increasing efficiency through automation, and as a result reducing costs and meeting some of the goals they set for themselves, and also adding new capabilities. We can look at some of these things in light of other areas where manufacturing is done. For example, look at the two images that are on the screen. The left is from about 1900. The right is from a automotive plant, a modern one. If you look at the black and white image, you've got two people working on a piece of equipment, on a car. All the work is being done by hand, and you expect variations in quality because of how people are doing the work, the mood they're in, how tired they are, how they feel. And the throughput's going to vary depending upon how things get done. In the image on the right, you expect to see the automobile moving down the line in a continuous fashion with parts being added, things being done to it, until you get final completion and testing of the unit. So automation involves streamlining. It also requires a careful analysis of how the lab process is being done. Systems have to be designed to be productive. It's not a case of simply bringing something in and trying to make it fit. And there's also a desire and a need for integration. The left image, there is no integration. The right, you have as much integration as possible. Taking all this together, you see the need for automation and why it's critical for laboratory work. But what we're seeing is exactly the same set of responses you expect to find in any production facility. Improvements would be seen in sample throughput, cost reduction, less variability in the data, reducing consumption of materials, and also more predictable consumption of materials because of the routine nature of automation and better use of people's talents. Let's take a look at that last point. We need to make it easier for people to use their skills and capabilities. Some of the surveys we've had have comments in them about people not liking the fact that their job is to move things from one piece of equipment to another. They want to use their heads, they want to use their intelligence. And by using automation, we can free them from a lot of the manual labor that's involved in laboratory work and let the intellectual work take over. We've talked a bit, or I've talked a bit about laboratory automation, so I think it's a point where we should take a look at exactly what laboratory automation is. Automation really focuses the discussion on the tools and the methods used to do the work. This is a diagram that was done by Eugene Garfield back in 1979. The circles represent various types of science. The lines show how they're related, the number of publications that went from one science and referenced another one. So you can see that chemistry and crystal structure are related, particle physics and nuclear structure are related. And if you look at these maps, these structures, over a period of years, you can see how new fields come up, old ones become diminished, and how the relationships between the fields change. This is what science is about. Laboratory automation is not about science. It's about how the work of science actually gets done. For many people, the kinds of things that are popping up on the screen represent what laboratory automation is. They look at it in terms of products, plate stackers, auto samplers, high throughput screening, laboratory information management systems, a whole range of hardware and software. The survey I mentioned a few minutes ago that came in an email probably focused primarily on products for their marketplace numbers. They didn't get involved with services or the engineering involved with the laboratory markets. And that's something we really need to deal with. Our definition for laboratory automation is this, and forgive me for reading it. Laboratory automation is the process of determining needs and requirements, Planning projects and programs and evaluating products and technologies, developing and implementing those projects according to a set of methodologies that results in the types of things that you need to have done in your laboratory, meeting the goals that you've set for them. It's process-oriented. It's engineering-oriented. The products and technologies used to implement these systems come from a wide range of sources that include hardware, software, robotics, laboratory information management systems, electronic laboratory notebooks, the whole gamut of things. In order to be successful, automation needs to be applied to a process. We've put a lot of stress on definitions because they're important. The wrong definition can limit your thinking. If your view of laboratory automation is things that move, liquid handling systems, auto samplers, that sort of thing, then you're going to miss a lot of the potential that can be met in your laboratories by looking at how other systems can be pulled together. Our definition will give you a wider field of view. It's a lab-wide system, lab-wide definition that brings in together all the activities that go on in laboratories. One of the results of lab automation is a conversion of processes from manual execution to machine execution. Having a well-defined process is fundamental to that success, and those processes should be the best ones possible. You need to make sure when you're working on this that you fix the process problems first. Otherwise, they'll simply become part of the work that you're doing. They'll become part of the automation. Lab automation systems include some things we've talked about last week and talking about again this week. Fully automated production environments, instruments, and computer system experimentation. I want to come back to this point for a moment, that the processes need to be the best possible. When you look at the processes that you want to automate, you need to make sure that the documented process has been thoroughly tested. And by tested, I don't mean simply saying, yes, it was copied from a publication, the publication was validated. What I mean is take the documented process and follow somebody around the laboratory who's actually doing that work. Make sure that everything that they're doing is part of the process, because very frequently people will make small changes to a process, little tweaks, that are critical to the success, but they never wind up in the documentation. And without that information, those little tweaks, knowing about it, you may wind up implementing the wrong process. You also have to make sure that it's cost effective, and then do the analysis work to make sure that the process can be automated, that there isn't something about the equipment that precludes that from happening. For example, take a look at this simple diagram. Image. How would you make one toothpick? Some people would say, well, you start off with a tree and keep on whittling until you're down down to one toothpick, or take a splinter and smooth it out and use it. Okay, that's one process. But suppose your goal was to make millions of toothpicks that sold for the price of $800 for 59 cents. The actual process that's used to make toothpicks is something that I would never have imagined. It involves taking logs, cutting them to uniform size, then shaving long, thin ribbons, feeding those ribbons into stamping machines, drying the stamped toothpicks, and then putting into packaging.
Some people use them to hold hors d'oeuvres together, while others make scale models of famous buildings and bridges out of them. And some people actually use them for their primary purpose, to remove food caught between their teeth. What are we talking about? Why, the humble toothpick, of course.
Logs. Lots of birch logs are delivered to this factory. They're the raw material with which toothpicks will be made. The heavy logs are lifted by grippers and placed into a debarker. Bark isn't part of the fabrication process and is recovered by this machine. However, the bark isn't thrown away. It's sold to a neighboring factory where it will be used as fuel. The debarker works in 2 steps. With 2 passes, it produces a log roll that's perfectly cylindrical and easier to mill. This particular log of wood is being transported to the next processing stage. This unraveling machine unravels the log as if it were a roll of paper, cutting it with 12 fine blades, each 1.06 millimeters thick and 6.3 centimeters wide. These same blades will be used later to cut toothpicks. Then these 12 blades, positioned side by side on the unraveling machine, will form rolls of strips called billets. The roller rolls up the cut strips, forming a billet. Completed strips, or billets, are taken out manually. Each billet weighs 1.8 kilos. The billets are carried to the puncher. The flat toothpick puncher cuts the billet strips into small, equal-sized pieces. The cut pieces come out at this end of the machine. The punch works very rapidly. Knives come down 2,000 times per minute to cut a total of 8,000 toothpicks in just 60 seconds. Cut toothpicks fall into this chute, then into a container. At this stage, they're soft. They have to be hardened in a dryer for 4 hours at 121 degrees centigrade. Then the toothpicks are transferred to the polisher. Talcum powder and friction help make the toothpicks perfectly smooth. This operation takes 4 hours. Toothpicks exit the polisher and pass through this sifter, which filters out broken ones. Those in good condition continue on to an air blower system. Damaged ones are rejected. Perfect toothpicks are placed onto 2 conveyors by an air blowing system. Drums at the end of the conveyors assure quantity distribution, then they're carried toward the automatic packagers. This machine counts the toothpicks. Boxes are made up, ready for filling. The number of toothpicks included in each box counts. The packager is calibrated to place 650 toothpicks per container, and it produces about 1,150 boxes an hour. It thus handles 747,500 toothpicks every hour. Some toothpicks are individually wrapped for distribution to restaurants and airlines. This machine wraps 1,200 toothpicks per minute. It automatically wraps, glues, and cuts the paper. This facility can manufacture the astronomical number of 20,217,600 toothpicks every day, and all this starting from a few birch logs.
This part of the image shows a log being cut. It's cut not only to length, but it's also trimmed to a uniform diameter, so that when the strips are shaved, they can be done uniformly to the same thickness. These are the strips here that are being fed through into a cutting machine that's used to go off and cut the individual toothpicks. So it's an interesting process and a fairly complex one. In implementing that process, the equipment's changed quite a bit from what you might have considered for doing a single toothpick. So how you deal with the process is important. You really have to do a thorough analysis to make sure you're doing the right process and you're doing it in a way that works. One of the things that caused a lot of failures in the early days of robotics is that people would look at a robotic system and said, we'll make it carry out a test exactly the same way a human would do it. And it didn't work. It didn't work because the machine was actually slower, people were actually faster, and it wasn't optimized. The equipment wasn't optimized for work, and the process wasn't optimized for the robots to work. In the diagram we talked about last week, the elements of laboratory technology, one of the points we covered was the issue of classes of laboratory automation. And we mentioned that there were three classes: computer-controlled processes, laboratory-assisted, computer-assisted laboratory work, and then scientific manufacturing and production systems. Computer-controlled processes is actually the earliest phase of laboratory work that involved computer systems. This is where the second phase of lab automation actually began. And the products that were being used were systems like LabVIEW for doing data acquisition and control, robotic systems, autosamplers, connected instruments, and data station combinations. The reason that it's the second phase is that the first phase actually took place in the 1940s through the 1960s, where automation was done using analog electronics. Recording spectrophotometers, which many of you may have in your laboratories and look at as being the common instrument, are actually an example of laboratory automation. Before they learned how to make recording devices, when you went off and measured a spectra, it was done one wavelength at a time with somebody making all the adjustments at each wavelength, recording the absorbance, and then moving on to the next wavelength. Recording spectrophotometers did all that for you. It automated that process. In addition, process chromatographs came out, which automatically took care of pulling the samples in, controlling the process, automatically attenuating peaks, and then recording the data, or actually the waveforms, on a piece of chart paper that somebody could go off and analyze later on. In the 1970s, we really started the serious work of modern laboratory automation with analog to digital converters doing signal processing and acquisition and experimental control, and then moving through what we have today. Those last two sections, the LIMS and ELNs, are examples of computer-assisted laboratory work. You're doing things with a machine that could be done by hand, and a few years ago would have been done by hand, but now is being done with the assistance of a database system to go off and to either acquire data or record it or help you analyze it. The last, scientific manufacturing production systems, consists of combinations of those first two classes depending on how your procedures put together, and it's designed to really deal with large amounts of samples. You're in a production environment. You're actually dealing with a manufacturing environment. When lab automation is introduced into a laboratory, you're really introducing a small-scale manufacturing operation. And the term scientific manufacturing was introduced to me by a gentleman by the name of Al Correa at Cambridge Biotech. The concept behind scientific manufacturing is a change in the way we think about laboratory work. It moves automation from dealing with tasks to improving the efficiency and productivity of lab operations. It provides a basis for understanding the importance of integration. And one of the things that we're sadly needing in general industry automation is standards. And it's one of the things that makes laboratory automation in the clinical industry successful. We really need to put a lot of stress on technology planning. If you look at a scientific manufacturing process, it's basically input to a process and then output. The inputs are samples and reagents. The process involves instrumentation, robotics, and people. And the result is either process samples or the knowledge, information, and data, which are the real results of laboratory work. That process is a science-based process. It involves method development, analytical techniques, assays, but to be used in an automated environment, they've got to be converted to an automated process and analyzed for the appropriateness for automation. So laboratory automation and scientific manufacturing is an implementation of a science-based products. And one of the things that we have to remember is that we automate processes, not things. Frank Zini, when he was in charge of Zymark back in the 80s and 90s, would start all of his classes with that statement. We automate processes and not things. You can put a robot in place, a robotic sample preparation system, but until the process is defined, the robot has absolutely nothing to do. When we look at these things, we can see a lot of parallels between manufacturing technologies and the things that go on in laboratories. In testing laboratories, the appropriate analogs for manufacturing technology are things such as long-term continuous systems, continuous improvement systems, evolutionary operations. What you're doing with those types of techniques is putting a system in place and then under controlled conditions making small changes to the systems to improve their operation, tighten results. In research and development, the appropriate manufacturing technology would be flexible automation, simply because you may be using sets of pieces of equipment together to provide an automated system that may not be of very long duration, as opposed to testing, where the duration is very long. We see the same types of discussions when people are talking with the FDA about quality by design approaches, where they're looking at ways of improving the way design is done for manufacturing. We can take the same types of things and apply them to testing laboratories, from analysis to reporting to going through the whole work of how systems are being designed. Success depends upon process management, integration, and standards. And none of this sounds like chemistry or whatever science is appropriate for your laboratory. But it is appropriate for automation. Remember, we're talking not about the science itself, but about how science is actually being done. We need to be able to answer some simple questions. Can the process be automated, and can it be done in a cost-effective manner? We can learn a lot from manufacturing, and one of the things, if you're looking for people to help you do this work, manufacturing is a good place to go. How you manage and apply automation, introduce process management techniques, and provide periodic reviews of the systems and their performance. Things such as statistical process control, evolutionary operations, and process monitoring can help you meet regulatory requirements if they're appropriate for your laboratories. One of the things that we see, process optimization in throughput, reliability, more robust systems, materials usage, and data flow. And one of the things we start to see in most work that's being done now is a movement from 100% manual methods in the laboratory to those methods being migrated to automated systems, and then eventually migrating out of the labs to in-process continuous automated testing. This is an area that's fairly active, both in FDA and EPA environments, where people are looking at continuous inline processing, process monitoring, instead of having samples continuously sent to the laboratory. We hit on it last week, and now we'll come back to this issue: the skills needed for work in laboratory automation. Adding automation to your lab's work is a cultural change, and people really need to be educated to be successful. That includes managers as well as individual contributors. When we look at people, we need to look at how work is going to change. What will people's jobs be in automated laboratories, and what are their job descriptions going to be? Background requirements, and what kind of education do they need? And again, we can get some guidance from this from people that have done work in clinical chemistry. There was some concern about how people's jobs were going to change there. Remember, clinical chemistry started their work in the 1980s. This paper came out, and it indicates that scientists' roles are going to change. And now, instead of simply carrying out test results, they're going to be there to guarantee the quality of analytical results, ensure pre- and post-analytical phases, provide continuous improvement to the interpretation and generation of data, in this case being used for patient management. And they'll participate more actively in the research to make sure that laboratory data is being used to its best capability. We've also talked to two people who are educators in clinical systems. One of them was trained in both chemistry, industrial chemistry, as well as clinical environments, and the other was strictly dealing with clinical environments. This is the clinical person. She said that she needed to understand how to troubleshoot instrumentation better, that the person not only had to understand the science, but had to know how to evaluate quality control results and have a quality assurance system in place to make sure that the test information was valid. Basically, the person was concerned more about monitoring the process than actually worrying about how testing was done. And that was echoed in this statement. This is a person who has both industrial as well as clinical backgrounds. Her chemistry background was taught how to generate results. The clinical side, she learned not only how to generate results, but to make sure that the process was working properly, that she got quality results, and could troubleshoot the process if something wasn't working well. The education that's necessary needs to move beyond the basic science. Chemists dislike the term cookbook chemistry, that you're doing everything according to recipe and all you're doing is just following a set of procedures with not much thought behind them. Well, one of the problems we're dealing with right now is the issue of push-button chemistry, where people use a piece of equipment, do not fully understand how it really works, put samples in, press a button, get numbers out, and trust them without questioning how they were generated. We need people that don't have to be programmers, but really understand how systems work, how the various control parameters that go into an instrument affect the results, and making sure they're working with ones that are optimized for it. We need to be able to think in terms of processes and systems. And one thing we'll get to in a moment is they have to have the right backgrounds. The idea of simply having general computer knowledge or office products for laboratory people simply isn't sufficient. This idea of a cultural shift is an important one to think about, because people are going to become uncomfortable about how things are going to change when they're faced with new tasks. How are they going to wind up using a new system? Are they going to be able to do it? How are they going to be trained? So you need to make sure you put programs in place that provide for training that is low risk. And we'll talk a little bit about that later on. This is a survey that we did of 88 job descriptions that was roughly split between managerial and non-managerial positions. The bulk of them came for the life sciences industries because that's where the hiring was done. And what we wanted to do was find out what kind of backgrounds were being requested for people working in laboratories with automated equipment. So we did it in two passes. We first went through and looked for some keywords, and then went back through them again and see how they turned up, how many turned up. The list on the left are the keywords that we found, and you can see the response. Even in an industry which is heavily regulated and uses a lot of automation, people's backgrounds really didn't reflect that need. The scary thing is that since we're talking about life sciences industries that are FDA regulated, only 20% of the management positions required a background or an understanding of regulatory requirements. I showed you this chart last week, and it's the same thing, that basically things have changed. Job skills have changed. That lab automation is essential for most labs, but not all. Skill set has changed. And then entry-level scientists are capable, and that is people with masters and above, are capable of working with the systems, but many of the people coming into the industry are not. People are going to spend less time dealing with tasks, more time managing processes and troubleshooting systems, evaluating quality, and understanding results. Systems like this are available. Now, what this is a test that goes on in food products for PCB analysis, particularly in fish. If done manually, the process takes a week. Done with this piece of equipment, it takes a day. Basically, it's an automated extraction chemical processing system. Same thing you'd find in any, not the same thing, but the same type of thing you find in almost chemical engineering. The chemist puts the samples in on one side. The processed extracted material comes out on the other side, and what their job is not to go off and do the actual assay, but to make sure that the equipment is working properly and performs the assay properly. Again, we're looking at manufacturing environments. Let's compare how manufacturing changes with how it affects laboratory operations. We're going to look at the development of manufacturing and production stages according to a set of criteria on the left side of the screen. And we're going to do it using a fairly simple problem for manufacturing. That is, producing shaped wood products. These are the kind of things you see on window trim, windowsills, and on cabinet doors in your kitchens. The diagram on the right shows the rails and stiles that are used to make cabinet doors, and you can see here how they're cut to fit together. Well, that's done with fairly interesting wood shaping equipment. At the simplest level, that stuff can all be done by hand, but it's slow. You use devices like the one shown on the screen to go off and shape wood. You repeatedly draw knives across the wood to gradually cut away the material you don't want to form the shaped pieces. It's a really slow and labor-intensive product. If you're a craftsman and you really want to get into woodworking, it's an interesting way to go. But if you're concerned about productivity, it doesn't work so well. The production cost is high, productivity is low. You have to be a skilled craftsman to understand how to make the adjustments and how to use the tools. Quality is variable depending upon who you are and how skilled you are. But the flexibility is very high. The same tool can be used in a variety of different ways to make different cuts. This is really kind of the cottage industry, where people are making small amounts of products for sale. If you want to improve your throughput, you can use a piece of equipment like this. This is an electric router, and it uses bits like these and like these to go off and make cuts at high speeds. The router will spin the cutters at about 20,000 RPM. These are the rails and stiles we looked at before, and these are the cutters that are used to go off and make them. When you use equipment like that, the production cost is still high because of the cost of the equipment. Productivity is improved because you can get through things a lot faster. You can make things in maybe 1 or 2 passes where it might take several dozen passes with a hand device. You need to be a skilled craftsman, but you also had to learn how to operate and adjust the tool. The quality is more consistent. The flexibility is high because you have a variety of routers available to you, router bits. So we're starting to get into the growth industry phase where you want to start making things but at a higher rate. If you want to produce things even faster, you use equipment like this. Each one of these is a router cutter, and this is a numerically controlled machine. You have a program that determines what bits are going to be used, how they're going to move. You put the piece of material on the table, and it cuts it all automatically to whatever shape you want. As a matter of fact, you can get in very complex shapes and even produce things like this reproducibly at a high rate. When we start looking at equipment like that, the production costs go down. Productivity is moderate. Skills, you're more of a skilled operator. You're more concerned about operating the equipment and making sure it's programmed properly than you are really worried about the wood product. Quality is much higher and consistent, and the flexibility, well, it depends on your programming. And finally, the next stage, the automated assembly line. Your production costs are lowest. Your productivity is high. The skills involved are those of an assembly line operator watching the production process, instead of worrying about the details of how you shape wood. Quality is consistent and high, but the flexibility is rigid. If you want to make something a little bit different, you've got to really re-engineer the process. In terms of the skills of the people involved, you're moving from skilled craftsmen to a skilled operator, with more and more attention being paid to the tool than it is to the actual wood itself. The individual craftsman, high cost, and as you move across to someone dealing with the automated process, the cost becomes down, and again, you see that change in skills. In order to make that system work, you've got to deal with process analysis, standardization of tools and materials, and it has to be designed to integration to make sure the system works. When we're talking about laboratory applications, we can see the same type of thing, moving from manual methods to systems where you have, for example, an auto system to assist in the work, to instrumentation that provides a sequential step automation for a given process, Carl Fisher titrations, for example. And then we have the automated assembly line type systems that we looked at earlier. And you can see pretty much the same behavior in terms of production costs, productivity, and skills required as you moved from one end to the other. You see manual testing primarily in research applications, and then as you start moving into more high volume testing, you're really dealing with the scientific manufacturing. And again, you have to be a skilled scientist here, and actually you've got to be a skilled scientist across the board, but the skills you're actually using are more operator and systems management. And this is what the clinical people found out. The two areas on the left are common in most industries and most lab work. We're still dealing with manual techniques and individual tools for doing the analysis. Manual techniques are what science undergraduates do. The systems on the right are areas where clinical chemistry comes in, high throughput screening, bioassays. Because of the standardization, they're able to take advantage of these higher levels of productivity. In research, we can see how things fall off. The research, the emphasis is going to be on manual techniques, but very little into the more heavily automated systems, except for things like high throughput screening. R&D testing, something similar. Quality control is where you really see the emphasis being put on automation. Again, it's all built on a basis of science. So we look at scientific manufacture, you see the same thing we see in any type of production environment, and changes in skills. Where the individual specialist was doing the work, the cost is high, the variability in the quality, and requires a certain level of skill. And then we add more and more automation to lower the cost, get better productivity. And we start achieving the things that we're looking for when we deal with automation. We started this presentation. The biggest issue is how we educate people. We're doing work with the University of Rhode Island. It's going to take a fair amount of time for this actually to come to fruition, but to start educating people on how to deal with automation. What's needed are lab people that are competent users of modern lab instrumentation systems, and a class of people we don't have, laboratory automation engineers, that are capable of planning, implementing, supporting systems, as well as developing products. What we're working with them is creating initially one semester programs for all science majors to get them up to speed on what modern laboratory systems look like. And then 2 levels of graduate programs, one directed towards the people who are going to go off and do the planning work, and then the second one, people going to do the engineering for new products. In the next session, we're going to be looking at the options for improving productivity. Between last week's session and this one, we've given you the basis for understanding what laboratory automation is all about, and now we're going to look at how we actually deal with the issues in terms of productivity. What choices you have to consider, what those choices are, and how workflow analysis enters into the picture. That's my end of the presentation. What questions do you have?
Hi, Joe. Thanks. So we've had a couple of questions have come in. One of them would be, what are the biggest hurdles in addressing lab automation successfully?
The 2 biggest issues are education, making sure that people really know what they're doing and can move beyond the basic science to really understanding how laboratory systems work and can be utilized. And the other one is this issue of standards. Right now there are no communication standards, there are no data format standards. Where standards have popped up, like things such as microtiter plates usage in life sciences applications, they've made a big difference. But they aren't available in the general laboratory applications, and as a result, until we get those standards put in place and people really start pushing for them and making them happen, we're going to have problems getting the level of automation we really want. There are a lot of little standards efforts going on, but what it's going to take is a community coming together and saying, all right, we need this stuff. Make it happen.
Okay, another question. If we're not familiar with process optimization and analysis, where can we go to get help?
Manufacturing people are really good at this stuff, particularly people who do chemical engineering, because they have to look at the same kind of things you're looking at. They have to look at a chemical process, a laboratory process, and then figure out how to scale it up and make it work. They're doing it on a very large scale, but the same thought processes, the same techniques, the same issues, the same skill set that they need to do that work can be applied to stuff that's being done in the laboratory.
Perfect. Another question that has come in is, how do we go about getting our people, our staff, educated?
Well, courses like this and the series that we're putting together here are good ones. We're putting together some additional programs that will get people educated. We're putting out a proposal. If you're interested in getting a copy, let me know. But we're putting out a proposal to put together a fairly robust program for education. Most of the programs that are available in short courses are product or technology specific courses. So those are useful, but you need the broad basis to get people, broad basis in laboratory applications and technology to really build that on.
Excellent. And there's still, I'm going to do a little plug, still time to register, some of your staff as well for these sessions. And then one of our final questions is, why has clinical chemistry been successful, and what can we do to duplicate that success in our labs?
Right. Clinical chemistry has been successful for a couple reasons. One, there's an industry-wide recognition that a problem had to be solved, and they stood up and did it. They did it not only in the development of standards for communications that I'd mentioned, but when it came down to individual techniques, they decided that here's how these techniques would be implemented. And I'm not talking about techniques on the instrument level so much, but as on the process level. So if there's going to be a certain type of analysis that was going to be done, it was determined what the best method of analysis was going to be. And then they went to the vendors and said, we want equipment built around these techniques, and the vendors did it. So you'll find instrumentation in the clinical environments that are tailored not just towards a specific type of measurement, but in terms of a specific process. And that's the kind of thing we need to get through. Now, in general laboratory work, there are lots of different procedures. But for a given industry, you'll find that those procedures tend to focus down to a smaller number. And if we came together and said, all right, this is the way to do it, and we want to build an automated system that's standardized, then we can start getting higher effectiveness and lower costs for automated systems.
Perfect. Okay, well, that brings us to the end of the questions and the end of today's webinar. Please consider reaching out to Joe directly, as obviously he's the true expert in this field. I'm sure everyone has gotten an email from him, so you should have his contact information. If not, you can definitely respond to the follow-up emails that will be sent out to you. The webinar video will be available for viewing for 2 weeks after the webinar has taken place. You will be sent a password to access that video because this was a paid-for event. Once again, I would like to thank all our attendees for taking time out of their busy schedules to join us today. We look forward to seeing you back here again in October. Thank you and goodbye.